So now that we have two ways of expressing vectors, we have geometric and algebraic. What we're going to do over the next two sessions is to play around with them. We're going to get basically the same application questions, and we're going to do them in the first session, we'll do them geometrically, and we'll see how that's done. In the second session, we'll do those algebraically, how we convert geometric vectors into algebraic vectors, okay? And we'll try to decide over the next couple of lessons which method is best for certain situations, for certain examples, okay? But let's take a look. All right, so we're going to go into basically a little bit of some physics, I guess, here, and that's what we're going to be using, the velocity and force. All right, so with velocity and force, vectors are normally described with the magnitude and direction. Okay, so we have that. In most cases, two or more velocities are going to affect the result, having a resulting vector. All right. You've got boats and water. We did that the other day. A lot of times, planes and wind velocity affects the final outcome of the velocity itself. Okay, so we know that we're going to be adding velocities together. Okay, same thing goes with forces. You know, two forces act on a body, two or more forces act on a body, right? Makes that body move a certain way. We have to figure out how that body is going to move. All right, so in the first example, we're going to take a look at basically this linebacker example. All right, football, why not? Okay, so two linebackers hit an unaware quarterback. Okay, they hit him at the same time. Unaware meaning quarterback's not moving. We don't have to worry about his or her velocity or force or anything like that. Okay, we're going to say is the larger linebacker hit the quarterback with a force of 350 newtons east. Okay, so let's just stop there and take a look. All right, first of all, 350 newtons east. What does it look like? I know you've got the diagram, it's almost showing there. All right, but 350 newtons east, you can just quickly say, well, that's obviously looking that way. That's east. And we'll say that that's 350 newtons right there. Perfect. Okay. Now, a smaller linebacker hits with a force of 200 newtons north. Again, sorry, northeast. All right. So we're compass directions. 200 newtons, a smaller directed line segment. Northeast means it's at a 45-degree angle to it, right? So there's the next one there, and that's 200 newtons. The magnitude, the length of the line segment, right? Find the magnitude of the resulting force in which the quarterback feels and the angle that the force makes with the larger linebacker's force. This makes it easy. It's basically what is the angle according to this going east. Okay, force there. All right. But let's take a look and see what we've got. How do we get this diagram where the forces are lined up tail to tail, which is a subtraction, into an addition, right? We have to move the forces so that they are lined up head to tail. All right. So I'm just going to move this over. All right. Give us a little bit more room so we can see it. East, 350 newtons. Start at the head, go northeast, 200 newtons. Okay. So we've got our resultant is there from the tail of the first to the head of the second. There's our resultant. We'll put that as magnitude, okay, of the resultant. Now, how do you solve any part of the triangle? Again, we talked about this yesterday a bit. To review, sine law, cosine law, sine, cos, tan, Pythagorean theorem, all that stuff, right? So in this case, you take a look at, do we know an angle that's inside of the triangle? Well, if we're given that the angle between the two are 45 degrees, because based on the compass directions that we had, all right, then that means the angle outside here is the 45 degrees. So what angle is inside? Well, it has to be 135 degrees because of the supplementary angles, right? You've got two sides with a contained angle. How do you solve? You solve using cosine law. All right, get that in our minds. This is what we're doing. So the magnitude, do it using the cosine law itself. Now, I've already put this down on the sheet. We can take a look at it. Okay, it's the idea, right? The idea is what we're looking at. In this case, I've got it as Q, my R, okay? We're using the cosine law. You see the 135 degrees in there. We put in our 350, our 200s, okay? And when you use your calculator, you solve. This is the magnitude that it feels. The linebacker feels that, okay? So 511. All right, standing unawares. So now what we're asked for is, what is this angle? Because we were told in the question, what is the angle according to the larger linebacker's force? Well, here's the force along here, okay? So we're looking at this one. Again, what do we now have inside this triangle, right? We have known side length, known angle. So this one's, we know the magnitude, we don't know the angle on the other side. We're going to use the sine law. We do the sine law in order to find the angle. So the thought process, why we're doing things, okay? Trigonometry, we got to use it in this vector world. So you can see how we set up our sine law. Okay, the sine of the angle we want over the 200 equals the sine of 135 to 511. All right, isolate approximately 16 degrees. So here's how we can state it. All right, here's the force that the quarterback feels at 16 degrees from the larger linebacker. Okay, understand those. And the key is, okay, you got to be able to do the algebra as well. I'm assuming you can do this. All right, grade 12s. All right, now let's take a look at this next concept. So what we have here, all right, is, and this happens all the time. You see it everywhere. If you walk into some stadium, you walk into a gym somewhere, you got a scoreboard that's hanging up somewhere. It's not moving. It's fixed. That means the force of gravity with the tension of all the cables holding on to the scoreboard and all that are fixed. They're equal to each other. They're equal and opposite. They're not moving. We are standing, or maybe a lot of you are sitting down right now. Well, your weight is being forced down by gravity, right? But the chair that you're sitting on is exerting an equal and opposite force to gravity, all right? And so that's why you're not moving, okay? So what happens is if all these forces work together, two or more work together, such that the object doesn't move, well, then you're in a state of equilibrium, is what we call it. The sum of the forces is equal to 0. All right, and that's the idea. What we name one of the forces is the equilibrium. It's the force that is equal in magnitude but opposite in direction to the resulting force. Okay, to the resulting force. Much like, let's say if those two linebackers hit the quarterback, but the quarterback was actually moving, with a force of 511, right, newtons. And instead of going the 16 degrees, that way, it was going in the opposite direction and coming this way, right? Nobody'd move after that. Boom, stop dead. Okay, everybody. So anyway, this is the idea. all right? If you add up, let's say F1, F2, okay, you're going to end up with, the equal and opposite force of F3 is the opposite direction. Add them all up, you get zero, the zero vector, okay? All right, so that's the idea. So this is what we're going to be taking a look at. And here's an example. This happens to be a scoreboard, and we look at it, we can see kind of the idea behind it. A scoreboard is being suspended from a ceiling by two cables that make angles of 35 degrees and 40 degrees with the ceiling, okay? The scoreboard weighs 3,500 newtons. Determine the tension in each cable. The tension is the magnitude, right? The magnitude of the force in each cable, okay? Draw the diagram to understand the situation. Okay, so when you're looking at something hanging like this, you see this type of diagram, all right? The scoreboard is this point mass, all right? We consider it the point mass right here. And again, gravity is forcing it down. All right, so 3,500 newtons down. We've got the two cables. One of them is at an angle with the ceiling. We know here's the ceiling. All right, at 35 degrees, and the other one is the angle at 40 degrees. How do we find the cables, the magnitude of the other cables? All right, and let's take a look and see how we can set this up. Realizing that the tension of cable 1 added to the tension of cable 2 is going to be equal and opposite basically the tension of this scoreboard, the weight of the scoreboard. Okay, equal and opposite. It's going to end up like this at 350 straight up. They have to be. So cable 2 is going to come out like this, all right? And there's the magnitude of cable 2. Cable 1 is going to end up right up there, and its magnitude, okay? Because it's equal and opposite. We'll have equal and opposite down here. If 350 is going down, you know that that's zero, all right? So let's start taking a look. How do we start to fill in all of this information? What do we know about this? Well, we know some angles. Where do the angles go? If this were pretending the ceiling, we know that there's a 40 degree right there, right? Well, cable 1 is 35 this way, right? And if that's the ceiling for cable 1, then it's 35 degrees right there. We're using the Z pattern. We can see that that's 35 degrees there as well. So that's a total of 75 degrees. Okay, so we can take a look at that, and that's 75. We'll just put this here, redraw, 75 degrees. All right, clean that up a bit. Okay, so far this is what we have. All right, now notice we have a triangle. We have to solve a triangle, right? If you take a look, we have an opposite angle and an opposite side length, right? We're trying to find out other parts of it. Do we have any angles in here? Do we have an angle in there? Do we know what this angle is? Well, if this is a 90-degree angle, we know that because it's vertical on the left-hand side, all right? 90, take away the 35, it's 55, right? What's down on this side? Well, we already knew here, if the 45 was there, this is 45 there as well, right? So this is a 45 degree, right? So we have all three angles. We just need to know the sides. Well, this is the idea. If we take a look at this as doing the sine law, right? Can we just say that the magnitude, the C1 magnitude, over the sine of 45 degrees is equal to 300, 3,500 the sine of, oops, I'm multiplying, divided by the sine of 75 degrees, right? So the magnitude of C1 is equal to the 3500 sine of 45 over the sine of 75. Okay? We can do very much the same thing with C2, but this one's over 55, right? We still have our ratio with 3500, and so the magnitude is 3500 times the sine of 55 degrees over the sine of 75 degrees. Okay? Understand how we're adding all these up, how we're putting these together. All right? I believe I've got this already on this side here. You can see. Okay? We're using sine law. All right? We could see that here. We're using the sine law. All right, here's the first expression. Now I've got 50 and 55 down in here and said, oh, I see. I put a 45 instead of a 40. That's what it was. So that's on this side here. We can see that's why it's the, did I go 35 and 40? There we go. So in this case, where's our 45? This one here goes to 50. And that means this is 50 as well. Just getting the right things there when I took it off. All right, I should have kept the 35 up in the top and the 40 down at the bottom there. So that should be the 50 there. Okay. Anyway, so the numbers are there. All right, and you can see the diagram that's set. You work out just do the math, put it in your calculator, and find out the two magnitudes through there. Okay. So with these questions, all right, I want you to take a look at these questions here. Work on them with this geometric. All right. Try to see you're looking at all these cosine law, sine law. If it happens to be a right triangle, it's right triangle. Okay, great. You can use the primary trig ratios. Okay. Now for one of the things, and I believe it's question 10 here, it's one of these standard physics questions with a ramp. Okay, and you have some box on a ramp that's stuck, right? And instead of going down, right, it stays fixed, which means you've got your equilibrium right there. All right. Well, how are the forces all acting together? When you start to put a ramp up, okay, the force is perpendicular to the ramp that bounces off of it, basically. I call it bounces off. It's not really bouncing off. But anyway, so you've got this perpendicular out, and these two forces here are equal and opposite to the force of gravity that's going down. Okay, so remember that when you're going through these questions, and then you'll be able to set up the diagram well enough.